This is the homework help video for physics, homework 5.1. I will do numbers 1, 3, and 4. 2 and 5 you can handle on your own. So for number 1 here, we're going to start with Tiger Woods hitting a golf ball. It has a mass of 0.045 kilograms. And it has a speed, or he gives it a speed, or velocity is what we'll use here, of 80 meters per second. So we know the mass and the speed, and it asks what is the impulse that Woods puts on the ball. What is the change in momentum, would be another way to look at that, that Woods gives the ball. So to do this, we remember that impulse equals force times time, but it also equals the change in mass times velocity. The ball's starting velocity is 0, so its initial momentum is going to be 0 also. So the impulse here is going to be equal to our mass times our velocity from right there. So all we have to do for this is take 0.045 kilograms times 80 meters per second, and that should give us an impulse of 3.6 kilogram meters per second. 3.6 kilogram meters per second. And for sig figs, let's assume there's a point there on the 80. I don't know if that was there or not. For number 3 here, we'll move on to number 3. We've got car companies that often test the safety of their vehicles by subjecting them to car crash tests as a way to test their passenger compartments. We've got a 1,200 gram or kilograms, so our mass equals 1,200 kilograms car, and it drives toward a cement wall with a speed or velocity of 17 meters per second. So we know mass and velocity, and the impact brings it to a stop. That's going to be our time in 9.00 times 10 to the negative 2 seconds. Again, our change in mv is going to be equal to F times t, or our impulse would be another way to say that. And remember here that our final velocity is 0, so our change in mv is going to be equal to those two, because it'll go from whatever the momentum is now to 0. So we can also plug in our time there and solve for force. So we'll take 1,200 kilograms times 17 meters per second equals force times 9.00 times 10 to the negative 2 seconds. As we solve that, all we have to do here is divide by 9.00 times 10 to the negative 2 seconds to get force by itself. And when we run through those calculations, we should get 2.3 times 10 to the 5th newtons for our force. So the force exerted on the car, or the average force exerted on the car, it would be 2.3 times 10 to the 5th newtons. That's number 3. I'll also do number 4 for you here. We'll move down just a bit. Number 4 is a little bit different. It kind of answers one of the questions we've had in class recently. And it talks about the most recent calculation for the population of the United States is 312 million people. So we've got 312,000,000 million people. And they all jump at the same time in the same place with an average force of 900 newtons. So we're going to take that times 900 point newtons to get our total force, which is going to be very big. It's 2.808 times 10 to the 11th newtons. That's going to be equal to our total force here. We're also asked, or given, a time. So our time is 0.10 seconds. And we know that the Earth has a mass of 5.98 times 10 to the 24th kilograms. And we want to know what would happen to the Earth if all of these people jumped with this force for that amount of time. What would happen to the Earth? Would it move? So, we're going to use the same equation that we used earlier. The change in mv, or mass and velocity, equals F times t. We know our force, we know our time, and we know our mass. So we'll find out the change in Earth's velocity if this were to happen. So we can put 5.98 times 10 to the 24th kilograms. Whoops, sorry about that. Kilograms times v equals 2.8 times, 2.808 times 10 to the 11th. Sorry, I'm struggling with my stylus here. Times 0.10 seconds. As we solve this, 2.808 times 10 to the 11th times 0.10 is going to give us 2.808 times 10 to the 10th. And that will be kilogram meters per second equals still 5.98 times 10 to the 24th kilograms times v. Now all we have left is to divide by 5.98 times 10 to the 24th kilograms, or the mass of the Earth. And our velocity, or the change in Earth's velocity, would be 4.7 times 10 to the negative 15th meters per second. So, would Earth accelerate? Would its velocity change? Yes. Would it be noticeable? No way, because this is super, super, super small. It would be moving at 4.7 times 10 to the negative 15th meters per second, which is hardly at all. I hope this helped. I will see you soon.